All right. If you've spent any time with Linux, you're probably pretty comfortable with the classic permissions, read, write, and execute. But what if I told you there's a whole other layer hiding just beneath the surface, a set of special permissions that are, quite literally, the keys to the kingdom? They solve some really common problems, but if you're not careful, they can also blow a huge security hole in your system. Today, we're going to pull back the curtain on these secrets. So let's kick things off with a classic Linux puzzle, one that every single user runs into. You, as a regular user, can change your own password, right? But the file that actually stores your password information is owned by root, and only root can write to it. So how on earth is that possible? How can you, without any special privileges, change a file that you're not supposed to be able to touch?
And here's the paradox laid out plain as day. On the left, you've got the etc shadow file. You can see right there, it's owned by root, and only root has write permissions. But on the right, you run the passw command, and boom, it works. That command has to write to the shadow file. This really shouldn't work, but it does, every single day on millions of machines.
Now, the solution to this isn't some super complex workaround or security flaw. Nope, it's a fundamental feature of Linux, a secret that's been hiding in plain sight this whole time. So let's unmask it.
The first clue is right here. Let's just run a long listing on the password command itself, and when we look at its permissions, something's a little different. You've got read-write for the owner, and then wait a second. Where the X for execute should be, there's an S. That little s is our answer.
That's it. Seriously. That one little character unlocks this whole mystery. It's not a mistake, it's not a typo, it is a special permission bit, and it completely changes the rules for how this program runs.
That SES stands for SUID, or Set User ID. And maybe the best way to think about it is it lets a program temporarily borrow the superpowers of its owner.
So here's the deal. When an executable file has this SUID bit set, it doesn't run with your permissions, it runs with the permissions of whoever owns the file. Since the password command is owned by root, for that brief moment when you run it, the program is executing with full root privileges. And that's how it gets permission to write to the etc shadow file for you. Pretty clever, right?
And you can actually set this yourself using the good old chmod command. The symbolic way is chmod u plus s. Or, if you're using the numeric codes, you just add a 4 to the very beginning. So standard 755 permissions become 4755 when you add SUID.
Now, SUID is the most dramatic of the special permissions, but it's not alone. Let's look at the other two, SGID and the sticky bit. These are all about teamwork and keeping things safe.
Next up is SGID, or Set Group ID. This one's really interesting because it does two different things. If you put it on a file, it's just like SUID, but for the group. The program runs with the group's permissions. But where it really shines is on a directory. When a directory has SGID, any new file you create inside it automatically gets assigned to that directory's group, not your own personal default group. This is a game changer for shared project folders, and setting it is pretty similar. Symbolically, it's chmod g plus s. With numbers, you just tack a 2 onto the front of the permission code, so something like 2770.
Okay, and our final special permission is the sticky bit. Now this one is just for directories, and it's a special kind of safety net. When a directory has the sticky bit, it means that even if everyone can write files into that directory, you can only delete the files that you personally own.
The classic example of this, the one you'll see on every single Linux system, is the /tmp directory. It's the Wild West. Anyone can create files there. But see that little T at the very end of the permissions? That's the sticky bit, and it's the only thing stopping you from accidentally or maliciously deleting someone else's temporary files. It keeps the peace.
To set this one, you use chmod plus T for the symbolic mode, or you add a 1 at the beginning of the numeric code. So a wide-open 777 directory becomes 1777 with the sticky bit.
So these permissions are obviously super useful. But, and this is a big but, SUID in particular comes with a huge warning label. Anytime you're temporarily handing out root access, you're playing with fire. And for an attacker, it can be a direct highway to taking over your entire system. I love this quote because it just nails the problem. SUID gives a program all of the owner's power. Not just the one specific thing it needs to do, but the whole shebang. It's a blunt instrument, and if that program has even a tiny flaw, that hammer can be used to smash right through your security.
So here's how the nightmare unfolds.
An attacker gets on your machine with just a low-level account. The very first thing they do is scan for any files with that SUID bit set. They find one, and they discover it has a common bug, maybe a buffer overflow. They then build a special payload that tricks the program into running their malicious code instead of its own. And because that original program was running as root, so was the attacker's code. Game over. They own the machine.
Okay, that's the scary part. But the good news is you're not helpless. You absolutely have the tools to manage this risk. The trick is to be proactive and to regularly check your systems for these permissions.
Here's your basic audit checklist. You can use the find command to scan your entire file system. To find every SUID file, for instance, you just run find/perm 4000. You should do this on a regular basis. And if you find a program with these permissions that doesn't absolutely need them, strip them away immediately with chmod us. It all boils down to that core security concept, the principle of least privilege. Don't grant any more power than is absolutely necessary.
And speaking of least privilege, the Linux world actually has a much better, much more precise tool for this job. It's a modern alternative to the SUID hammer, and it's called Linux Capabilities.
This slide just says it all. If SUID is the hammer, capabilities are the scalpel. Instead of giving a program full root access, you can give it just the one specific capability it needs. A great example is the pin command. It needs to do one privileged thing, open a raw network socket. Instead of making it SUID root, we can just give it the cap_net raw capability. It gets exactly what it needs and absolutely nothing more. It's way more secure.
When you get right down to it, special permissions are all about this constant balancing act. They enable crucial functions, things we need to do every day, like changing a password or working together on files. But every single time you set that SUID bit, you're creating a potential risk that has to be carefully managed.
And that really leads to the final question I want to leave you with. These permissions, SUID, SGID, even just lazy 777 permissions, they're often a trade-off. We use them because they make life easier, they make things work, but they always increase your attack surface. So take a moment and think about your own systems, your own projects. Where is that little S or T hiding that doesn't really need to be there? Where have you maybe chosen convenience over security?